Have you ever just asked an AI assistant to, say, plan an entire international trip for you? In a matter of seconds, it checks your location, books a flight, and drafts up a daily itinerary. It honestly feels like absolute magic, right? But behind all that magic is a largely invisible engine called the Model Context Protocol, or MCP. It's this rapidly emerging standard that basically allows AI to connect to external tools and actually get things done in the real world. But here's the catch. While MCP is completely transforming how we automate complex tasks, it's also opening up some massive hidden security dangers. So welcome to this explainer. Today, we're taking a hard, objective look at the structural flaws inside this AI protocol, drawing directly from recent cybersecurity information released by the NSA.
So here's our roadmap for today. First, we'll meet the Model Context Protocol. Second, we'll expose its security blind spots. Third, we'll examine some real-world AI exploits. And finally, we'll cover the blueprint for securing the AI frontier.
All right, let's kick things off with Section 1, Meet the Model Context Protocol.
Okay, let's dive right into this and see exactly how an agentic AI travel assistant actually uses MCP under the hood. So at the very top of the workflow, you have the user ACK or UI. That's where you're typing in your prompt. This request goes down to the large language model, the LLM, which figures out what you want. But, the LLM itself can't actually book your flight. It has to talk to the MCP client library right below it. Think of this client library as the middleware. It translates the LLM's requests into MCP protocol messages and then routes them out to various MCP servers. Those servers act like orchestrators, matching incoming requests to really specific tools, like a travel planner, a geolocation service, or an airport database. The tools do the heavy lifting, grab the data, and send it all the way back up the chain to you. It's a highly flexible, incredibly powerful system, but as we're going to see, that flexibility is exactly where the problems begin.
To truly understand the risk here, let's compare traditional protocols with MCP. In a standard cybersecurity setup, the client simply asks the server for data. Think of it like a waiter bringing you a menu and then bringing you your food. You just stay safely seated at your table. But MCP completely reverses this familiar pattern. In MCP, the server often queries and executes actions on behalf of the connected client. It's as if that waiter didn't just bring you food, but actually walked right into your own kitchen, opened your fridge, and started cooking the meal themselves. This inversion of the traditional client-server relationship creates entirely new, largely untraced attack paths, simply because you're giving external entities a direct line right into your internal environment. And just like that, we're shifting from the incredible promise of MCP right into its very real structural flaws.
Which brings us to Section 2, the security blind spots.
According to the NSA, MCP's rapid proliferation has completely outpaced its security model. Because a lot of implementations lack role-based access control, an MCP server literally can't distinguish between a harmless read command and a totally destructive delete command. And its lack of boundaries is made even worse by insecure context serialization, which allows attackers to inject malicious code directly into structured data. Plus, because there's missing token lifecycle management, if an attacker intercepts a token, they basically hold the keys indefinitely. No expiration date. Worse still, a trusted server can silently change its capabilities in the background, bypassing poor approval workflows to access your sensitive data without ever prompting you for informed consent again.
So the crucial point is how all these flaws combine to create one massive, critical vulnerability: unverified task propagation. This happens when tasks are passed between MCP servers or agents without any proper validation of where they came from or what they actually intend to do. In an AI workflow, agents are constantly passing tasks to other agents, and because of how MCP is designed, there is a super dangerous level of implicit trust built in. One agent just assumes the output of another is perfectly valid. Because context windows overlap and blend across all of these tasks, sensitive data can leak out, or malicious instructions can propagate in, all the way down the chain, completely undetected by your traditional cyber defenses. Now, you might be sitting there thinking this all sounds a bit theoretical, but believe me, it is absolutely not. Let's look at Section 3, Real-World AI Exploits.
One of the most fascinating and honestly chilling exploits identified in the source material revolves around something called tool invocation path confusion. See, some MCP orchestrators are designed to just automatically resolve tool names from public registries or local modules, and this creates a naming collision vulnerability. It is shockingly easy for attackers to simply manipulate configurations or inject similarly named tools right into the environment. Because MCP clients often lack the ability to specify unique identifiers for these tools, the system gets confused. It accidentally loads the attacker's malicious code instead of the legitimate tool you actually wanted. The entire workflow gets hijacked simply by playing around with naming conventions. And this brilliantly illustrates how attackers can weaponize these systems, just like we saw in a documented real-world exploit involving the messaging app WhatsApp. Researchers tested a trusted third-party MCP agent that was used to enhance chat capabilities. Here is exactly how the trap works. Step 1. A malicious MCP server connects to the system, advertising a perfectly benign instruction just to hide its true intent. Step 2. Once it's installed and trusted, it quietly switches its descriptions to malicious instructions. Step 3. Because the client is now tethered to this rogue server, it is coerced into exposing actual WhatsApp message data. All of this happens without the user ever receiving a single notice or approval prompt. Wild, right? And we're seeing a similar disregard for standard security hygiene across other major platforms too. Take GitHub MCP tools, for example. Users were granting blanket access for tools to just act on their behalf. Without granular controls, malicious tools could read sensitive code from a private repo and just publish it publicly without the user having a clue. Or consider the recently patched vulnerability, CVE 2025-4956, found in the MCB Inspector toolchain. This testing product accepted inputs so freely that attackers could actually trigger remote code execution simply through crafted messages. It's absolute proof that basic software vulnerabilities from a decade ago are resurfacing entirely because these new AI toolchains are just overlooking established security practices.
Okay, time for some solutions. Section 4. Securing the AI frontier.
The NSA's core message here is that you have to enforce strict trust boundaries. You build this defense in layers. First, start at the gates by validating all inputs against strict schemas. Make sure they actually fit the expected intents. Next, contain the blast radius by sandboxing tool execution with frameworks like AppArmor or SE Linux, which prevents lateral movement across your network. You absolutely must segregate your environment, aligning tools with distinct data classification zones to keep those public tools far away from your highly regulated data. In transit, don't just rely on the transport layer. Cryptographically sign your JSON payloads to prevent any tampering. And finally, for your most sensitive, private data, your default should be running a local instance of your MCP server to totally eliminate external data leakage.
Now, what's really interesting about this slide is that it requires a complete paradigm shift for AI security. The NSA report emphatically states outputs from tools and models should never be treated as implicitly trusted, even if they originate from previously vetted components. Let that sink in. You must treat every single output as an untrusted input for the next phase. If you aren't actively filtering and inspecting what your AI tools are passing down the chain, you are leaving yourself wide open to cascading prompt injections and semantic manipulation that can silently hijack your whole system. Zero trust is the only way forward. As we wrap up this explainer, you really have to ask yourself one question. Is your AI agent leaving the back door open? The Model Context Protocol is an undeniably incredible leap forward for automation, finally giving our AI tools the ability to seamlessly talk to one another and act on our behalf. But that seamless connection fundamentally inverts traditional security models. If you're building, deploying, or frankly just relying on agentic AI workflows, you can no longer assume that internal task delegation is inherently safe. It's time to audit your tool chains, apply those granular access controls, and stop treating AI output as inherently trustworthy. Thank you so much for joining me to explore this critical source material. Now go take a much closer look at what your AI is really doing in the background.